Okay, last time we started our discussion on transformers, right? We started with linear transformer. Where is it? Let me go to that page first. It's too much. Right here, right? So starting from this page, and then we talked about some application side of the transformer, and then a linear transformer, right? Is the first type of transformer we discussed, right? Properties of linear transformer, and then equivalent circuit. But just in case you are dealing with a circuit with a linear transformer, then you could convert the linear transformer into either T equivalent circuit or pi equivalent circuit, right? And before that, we also looked at reflected impedance of a linear transformer, how you can actually change the value of the secondary side impedance to the primary side, right? That's called reflected impedance. And here's the T and pi circuits, right? Right there, right? The T and the pi circuit of linear transformers. And then once we're done with that, then we went on to review ideal transformer, which is the second type of transformer, right? In ideal transformers, we got rid of M and we use turns ratio instead of M. So we are using N, the lowercase n, which is for turns ratio, as opposed to using the mutual inductance M, right? So and then we looked at the definition of the turns ratio, which is N2 over N1, right? Which is related to V2 over V1 and I1 over V2, I1 over I2. And then we learn how to determine the signs of the turns ratio. That would depend on how you define voltages and currents, right? Right here. And these are the examples we went through last time, right? In order to determine again the signs of the turns ratio as they related to as it relates to voltage ratio as well as current ratio, right? Yeah. So the next section is on transformer rating. Any questions before I start the new section? Okay, if not, so transformer rating is typically given in one of two different units. The first one is kilovolt amps or volt amps, right? So apparent power. And the kilovolt amps or apparent power rating is typically given for big transformers, right? Transformers that are being used for the electric power grid for utility companies, right? They use big transformers, and so these transformers are rated at kilovolt amps, right? And the small ones, the small transformers, the one that you can buy to plug into the wall plug, for example, that would be rated in watts, right? So small transformers in watts, big transformers are in kilovolt amps, right? And the reason why the big transformers are given in kilovolt amps because of the fact that it is big transformers, right, made of big windings, big wires, right, big coils. So those give a significant portion of reactance inside the transformer. So not just resistance of the winding, but also the reactance becomes more of a significant portion of the impedance. That's why they use apparent power rather than real power, right? So kilovolt amps instead of watts. Here's an example of a picture of a transformer that I took when I visited the substation a long time ago. This is a single phase big transformer, right? As you can see from the rating right there, right? Can you see 370,000 kVA? That's big, isn't it? So that's the same as 370 megavolt amps, right? Huge transformer, right? So as you can see, the unit is kilovolt amps for this one. And this one has 3 windings, 1 high side and 2 low side windings. Okay, so 3 windings. Any questions on the transformer rating? Very short section. If not, let's move on to the next section. Actually, I have examples. The first example, determine the turns ratio of a 5 kVA, 2400, 120 volt power transformer. So we look at these numbers, right? First of all, you can see the rating right there, right? That's the apparent power rating, right? As rated. And then the second set of numbers, you see the voltage rating on the primary side. So let's call it V1, right? And then the voltage rating on the secondary side, call it V2, right? So from here, I can tell that this is from the voltage ratings right here. I can tell that this is a step down, right? Because the primary side is 2400 and the secondary side is a lower voltage, 120 volts, right? So it's stepping down, right? Voltage from 2400 to 120, right? So yeah, again, just by looking at these numbers, I know this is a step down. And it's asking for turns ratio. So turns ratio is equal to N2 over N1. But I don't have the turns ratio. I don't have the number of turns here, right? They're not given. But luckily, we know that N is also equal to V2 over V1, right? Which is also equal to I1 over I2, right? So depending which ones are given in the problem statement, you can either currents or voltages, you can then find the turns ratio. You don't have to know the number of turns. Right? So here, I know V1 and V2, V2 being 120, and V1 being 2400. So therefore, the turns ratio is 1 over 20, or 0.05. Right? And as I said earlier, this is a step down. Any questions? Okay, if not, next example, 480, 2400. Right away, you can see this is a step up, right? A step up transformer. How do I know that? Well, because the primary side is lower voltage, the secondary side is higher voltage. So from low to high, that's a step up, right? Delivers 50 kilowatts, right, to a resistive load. Calculate the turns ratio, the primary current, and the secondary current, right? Again, turns ratio is N is equal to N2 over N1, right? And so part A should be easy, right? To get it from the voltage, V2 over V1. So 2400 divided by 480, that gives you the turns ratio, which is right here, at 5. Right. Part B is asking for the primary current. All right, so primary current. Let's look at what's given first. We have V1, that's given, right? That's 480. We have V2, that's given, right? 2400. Then we have 50 kilowatts. If you read the problem statement, the levers, right? The levers 50 kilowatts to a resistive load. So that means that would be P2, right? Power delivered to the secondary side. So that's given, right? Okay. Now, part B is asking for current, right? I1. So it's asking for I1. How do we find this? Well, I know if I can find S2, then I can find S1. If I can find S1, then I know that S1 is equal to V1 RMS times I1 RMS. Since I know since I know V1, if I know S1, then I could find I1. That's kind of like the process here, right? So do I know? So the key here, do I know S2? Not directly, but we know it from the fact that P2 is 50 kilowatts, and it says resistive load, right? And we learned from chapter 2, I believe, right? That if you have a resistive load, right, that means power factor is equal to 1, right? That means Q is equal to 0, basically, right? If you have purely resistive load right there, that means Q is equal to 0, right? So if you draw the power triangle, just refresher here. That's P, that's Q, that's S, right? Okay. Now, if you have a purely resistive load, that means Q here is equal to 0, right? And if Q is equal to 0, what is the power factor angle here? The power factor angle is R cosine of the power factor, right? And if Q is equal to 0, that means power factor is equal to 1, right? So power factor is equal to 1. That means the angle would be 0 degrees, isn't it? Right? So 0-degree angle. So again, if you go back to the power triangle, if theta is equal to 0, what happens with the power triangle? If theta is equal to 0, that means, or likewise Q is equal to 0, that means P is equal to S, right? So that's how I get S2. Since I know P2, right, and I know that power factor is equal to 1 because it's purely resistive, that means P2 is equal to S2, right? And then what is S2 equal to? S2 is equal to V2 RMS times I2 RMS, right? Do I know V2? The answer is yes, right? V2 is given right here. Do I know S2? Yes, that's just equal to P2. That's the 50 kilovolt amps or 50 kilowatts, right? That's the one that's given. So since I know S2 and V2, I can solve for I2. Right. Oh, that's actually part C, sorry. But part B is asking for primary side. If I know S2, that means I know S1, right? Because S1 is equal to S2. One of the properties of ideal transformer is that apparent power of the primary side is equal to the apparent power of the secondary side. So once you know S2 from 50 kilowatts, right, from here, then that same number is equal to S2. And it's equal to S1, S2 is equal to S1. And once you know S1, then you know that S1 is equal to V1 RMS times I1 RMS, right? Okay. So from here, I can find I1. Right here, part B. S1 is equal to S2 is equal to I1 times V1. I know what V1 is. I know what S2 is, which is equal to S1, right? That's 50,000. So now I1 is just 50,000 divided by 480. That gives you 104.17 amps. Okay, and then part C, I already explained earlier, right here. Once you know S2 from P2, right? Then that's going to be equal to V2 RMS times I2 RMS. Since I know V2, I know S2, then I can solve for I2, right here. Are there any questions on this? All right. If not, let's look at the next one. Do transformers come with more than just 2 windings? If so, what do we use them for? The answer is yes. Some examples. This transformer that is connected to your house, for example, actually has 2 windings with a center tap that looks like almost you have. It looks almost like you have 3 windings, right? Right here. So you have the primary side and the secondary side, and the secondary side has a center tap, right? So that means you have practically 2 windings on the secondary side. See that? And yeah, the transformer that is sitting on the power pole around your house, right? Like right by the street in your neighborhood, it has a transformer that is connected to your house, right? That provides power to your house. And usually from that transformer to your house, they would run 3 wires, right? For line 1, line 2, right here, line 1, line 2, and the third one is the neutral wire, right? And if you couldn't find any power pole in your neighborhood, That means these transformers are usually underground if it's not on the power pole, right? So they're underground, and maybe you can find like a green box sitting right by a street in your neighborhood. So inside that green box, that would be the transformer for your house and for your neighbor house. Um, yeah, usually one transformer is connected to multiple houses, maybe 50 houses. But in any case, underground or not, or sitting on the pole, it would have one single winding on the primary side, 7200 volts, and another winding on the secondary side with center tap, right? Why do you need the center tap? So that you can actually run two different voltages inside your house, right? You could have the 120 volts, right? So going from any line to the neutral, so any line to the neutral right here, that would give you 120 volts. See that? 120 volts. So this would run, for example, lightings, the voltages that would be connected to your wall plugs, to the standard wall plugs, that would be 120 volts. Then why do we need line to line? Well, that's going to be 240, right? So if you do line to line instead of line to neutral, you get 240, twice of 120. Why do we need 240? Well, because some of the loads in your house are big loads, right? Washing machines, for example, right? Dryers. Those may require higher voltage, right? So if there are big loads, then they will be connecting it to the 240 from line to line, just like this. Okay. Any question on that? Any questions on this? If not, this is an example of a transformer, a small transformer that has multiple windings. In fact, if you look at the circuit diagram of this transformer, it has 6 windings. 1, 2, 3, 4, 5, 6. Right? You can see from the number of pins right here, 6 times 2, that would be 12. Right? So it's numbered 1 through 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 until 12. Right? And you can see that pin number 1 and 12, that's connected to one winding, 2 and 11, another winding, and so on and so forth, right? But here you have 6 windings. So what's the purpose of having multiple windings here? Many purposes. First one is to be able to supply multiple loads. So imagine if you have a transformer with multiple windings such as this, then you can connect one single source, right? And power or supply power to multiple load. See that? So that's one objective of multiple windings. Only a single source can power multiple loads. That will be convenient, right? Rather than having one single source for every load, you can have one single source for more than one loads, right? If you have multiple windings in the transformer. Okay, so that's the first objective or first use of multiple windings. Are there any other uses? The answer is yes. That'll be next. So what if you want to increase the current rating of the transformer? So if let's say from one single winding, you can only get 1 amp, right? That's only rated at 1 amp. But let's say that the circuit requires 2 amps instead of 1 amp at the primary side. So what you can do here is that you can connect another winding that also has the same rating of 1 amp, right? And then you would connect them in parallel, like this, right? So if you do it this way, now the current here that you can put in is 2 amps, right? Because it splits into 2 windings, right? So that's an increase in current rating. Again, by connecting multiple windings in parallel, you increase the current rating of the windings or of the transformer, I should say. All right. Any question on this? Another use of multiple windings to increase inductance. Let's say that for every single winding, you get only 1 microhenries, let's just say. However, let's say that your circuit requires six, or not six, let's say it requires 2 microhenries instead of 1 microhenry. What do? Well, if you have another winding in the transformer that also has 1 microhenries, then all you need to do here is to connect the two in series like that, right? So the total winding would be roughly 2 microhenries from here to here. Roughly, okay. If it's ideal transformer, it is going to be 2 microhenries. If it's not non-ideal, then it would depend on the dotted terminals. Remember, there's mutual windings. So it's going to be roughly 2 microhenries. Any questions on this? So there's another use. Here, it shows that all 6 are connected in series. See that? Okay. And if you look at the equation, it's actually more than 6 times. It's 6 squared. Right? That's from the mutual windings, right? So it's actually much more than just 6 times the individual windings. Okay, that's another use. But then this next one has to do with turns ratio. Right? That's another use of multiple windings. If let's say you want to have, out of the 6 windings, you want to have 1-to-1 ratio, then you can just simply use 1 winding for the primary side and only 1 winding for the secondary side. If let's say you want to do 1-to-5, right, such as this example, right, what do? Well, you use 1 winding for the primary side and then 5 windings in series on the secondary side. So by doing so, you have 1-to-5 turns ratio, right? So that's another use of having a transformer with, excuse me, with multiple windings. You could actually have different turns ratio depending on how many windings you connect in series on the primary side and secondary side. Can I do 2-to-2? The answer is yes, because you have 6 windings, right? Can you do 4-to-2? The answer is yes. Can you do 5-to-2? The answer is no, right? Because you're only limited to 6. If you do 5-to-2, then it requires 7 windings, right? Now you get the idea, right? Any questions on this? If not, let's move on to the next section. So you actually seen this concept before. It's called reflected impedance with a linear transformer. Remember, you be able to reflect impedance on the secondary side to the primary side, right? We can also do the same thing for ideal transformers, right? The reason why we need reflecting impedance, sometimes it is easier for us to just reduce the circuit into a single loop circuit. If you have a circuit such as this circuit right here, right? Let's call it Z1, Z2, and here's V1. If you have a circuit like this, then one of the ways to solve for, let's say, currents in the circuit would be using 2 loops, right? So there are 2 loop equations, from loop number 1 and loop number 2, right? Which is fine, but then keep in mind that you have turns ratio here, right? So there some complication here, because not only that you have to do 2 loops, but also you have to pay attention to the turns ratio, and also you have to pay attention to the signs of the turns ratio. Remember from on Monday, right? We learned how to determine the sign of the turns ratio, depending on whether or not current enters or current leaves, right? And voltage is at the dotted terminal, what have you, right? So there are more complication than just the 2 loops, right? So it'd be nice if you could somehow reduce this circuit, right? Reduce it to 1 single loop. Imagine we could do this. There. Okay, that would be nice, right? Except this one becomes G2 prime. So now you only have one current, right? You only have one current. And then you don't need to worry about n anymore. You don't need to worry about the signs anymore, right? Just solve this one loop equation. You get I1, right? And then from I1 you get I2, and so on and so forth, right? So then, is it possible to reduce from two loops to a single loop or a transformer circuit? The answer is yes, right? By using or applying the reflected impedance method, right? So from two loops, right, such as this one. So this one similar to what I drew, except this one has the second voltage source, right? So basically reduce this to a single loop circuit, right? In order to do that, in order to apply the reflected impedance, if you look at the circuit again, I could actually do it in two different ways. I could, for example, reflect all the components on the secondary side to the primary side, right? If you do that, that's called primary rule, right? So primary rule is when we reflect all the components on the secondary side to the primary side, right? That means the primary side components will be staying the same. You don't change their values. So V1, VS1 stays the same, Z1 stays the same. And Z2, since you reflect it to the primary side, becomes Z2 prime. VS2 becomes VS2 prime, because again, you reflecting it to the primary side, right? So this is primary rule. Any question on the objective of the primary rule? Whereas secondary rule is the opposite, right? How I would reflect components on the primary side to the secondary side, right? If that is the case, then values on the secondary side, Z2 and VS2 would stay the same, whereas values on the primary side, VS1 and Z1 would change, right, to their reflected values. So Z1 becomes Z1 prime, VS1 becomes VS1 prime. Any question on this? All right. So that's what I have right here on primary rule and secondary rule, right? Again, primary rule in which the secondary side is reflected to the primary side, or the secondary rule in which the primary side is reflected to the secondary side. With the primary rule, so let's start with the primary rule. As I said earlier, the primary side stays the same, right? But the secondary side components would change. For example, the impedance, right? Going back to this picture, how do you reflect Z2 to the primary side? How do you do that? Right here, you simply divide Z2 by n squared. What is n again? That's the turns ratio. So don't forget to square it, right? So Z2 over n squared, right? That's how you find Z2 prime, the reflected impedance of Z2. And then voltage and current would also be reflected by the turns ratio, right? As you know, V1 over V2 is equal to N1. Well, V2 over V1 is equal to N, is equal to N2 over N1, is equal to I1 over I2, that's equal to N, right? So you can just use this equation to reflect the voltages and the currents, right? So depending on which one you're actually moving, is it V2 or V1? So if you apply the primary rule from this original circuit right here, now it changes to the equivalent circuit from two loops. There are two loops, 1, 2, to only one loop, right? Just nice, right? That's easier to solve than the two loops, right? And now you can see Z1 and Z2 are in series. You can just add them up, right? Z2 becomes Z2 prime, don't forget, right? And then VS2 becomes VS2 prime. And I2 also becomes I2 prime. Notice that I2 prime is equal to I1 as well, because they're in series now, right? Any question on this? How about secondary rule? We'll do the opposite, right? How do you reflect from Z1 on the primary side to the secondary side? How? By simply multiplying it with n squared. So that's the inverse of the other one, right? Remember, from secondary side to the primary side, you divide by n squared. But now, since you are doing the opposite, primary to secondary side, that's why you multiply by n squared instead of divide, right there, right? So Z1 prime is n squared times Z1. And the same thing with voltages and currents. You do the turns ratio relationship to find the reflected value for the voltage and the current. So after you apply the secondary rule, oh goodness, you get this circuit right here, right? So Z1 becomes Z1 prime, VS1 becomes VS1 prime, I1 becomes I1 prime, whereas the secondary side component stays the same. Are there any questions on this? No? Yes, go ahead.
For the voltage source, you just apply like the same equation for secondary rule transformation, like the reflected equation.
Yeah, don't do the n square. You do this equation.
Oh, okay, sorry. Yeah, I see now.
Yeah. Okay. Yeah, do the turns ratio equations. Yeah, the n square is only good for impedance, reflected impedance. All right. Any other questions? If not, let's look at this example. Draw the equivalent circuit using primary rule and secondary rule. Right. So let's do the first one, primary rule. But before I do that, let's look at the circuit first. The original circuit, as you can see, has a transformer, 2 loops, right? Let's reduce it into 1 loop. So primary rule means what? Means I would reflect all the secondary components to the primary side. In this case, not that, only one component, which is 2 ohms, right? And the turns ratio is, what is the turns ratio here? N is equal to N2 over N1, which is equal to 1 over 4, right? That's our N. All right, so by applying the primary rule, I am reflecting 2 ohms to the primary side. How? Dividing 2 ohms with N squared right here. Right? And I get 32 ohms. So once I've done this, basically what I've done is this: I transform that initial circuit into an equivalent circuit that looks something like this. Right, that's the primary side, stays the same. And then on the secondary side, instead of having the transformer and the resistor, I just replace it with one resistor that is now 32 ohms, right here. So it's the reflected value, right, of the resistance on the secondary side to the primary side. You can see how the circuit now becomes easier to solve, right? Only one loop, and you can solve for I1 this way by Ohm's law, right? So once you get it into this equivalent circuit, you can tell easily that these 3 components are in series. You can reduce it into one single impedance right there. So you just sum them up, right here. You get our total impedance on the primary side, okay, which includes, again, reflected resistance from the secondary side. Again, by having this simpler circuit, equivalent circuit, I can now, for example, solve for I1, if that is what you're looking for. Right. Any question on this? Okay, if not, let's do the second part, part B. So part B asks for secondary rules. So the secondary side remains the same. The primary side is reflected to the secondary side, right? So now on the primary side, I have multiple components, right? I have the voltage source, I have the impedance, right? So I need to move those to the secondary side, right there. How do I do that? Well, for the impedance, you multiply by the turns ratio, which is right there. Turns ratio is 1/4. Right? So then you have the reflected impedance on the secondary side. Right? Basically, what I'm trying to do here, I'm trying to create an equivalent circuit that looks like this. V1 prime, VS1 prime, and the secondary side stays the same, which is, what was it again? 2 ohms, right? Right there. Now, what about VS prime? Right here, you can see that VS prime, VS1, I should say. Actually, VP, I call it VP now. Right? VP prime, which is the reflected voltage from the primary side, is equal to VP times N, right? Okay. Right, that's from here, from that equation, right? That V2 is equal to V1 times N. Well, our V2 is our reflected value, right? So in our case, this V2 right there is our reflected value, VP prime. And then V1 is our original voltage, VP, right? Okay, so that's VP times N. That's going to be 5 at 0 degrees. Any question on this? So VP prime is equal to VP times N. Okay. So once I have this circuit right here, I can reduce it more, right? We can see that these two are in series. So I could reduce it more, just add the two, then you get the total impedance, equivalent impedance, which is right here. And the circuit now becomes this circuit. All right. And from here, I can get, for example, the current, right? Any questions on this? So again, that's an example on how to apply primary rule and secondary rule. This next example, yeah, first of all, if you go to the next page, I made a typo here from the previous section. I found out that there is a typo. This negative sign is actually not there, so it should be positive. So just get rid of the negative sign, like this. Okay. I'll explain later. But for now, go ahead and get rid of those negative signs for this equation right here. Okay, and let's go back to here first, or yeah, go back to the circuit. Determine I1 and I2 in the circuit below. So I have a circuit with a transformer, ideal transformer with a turns ratio of 1 to 2, right? So turns ratio here is 1/2, right? And 2/N1. There, right? And then you can see that on the primary side, I assume that current direction is clockwise. So I1 is clockwise. I also assume that I2 is clockwise as well, right? And then we'll see whether or not these are correct directions, right? Okay. And then it's asking for the values of I1 and I2, right? And you can see that voltage phasors is 20 at 0 degree angle, right? All right, so then there are different ways of solving this problem. I could, for example, just stick with the two loop equations. If you prefer, go ahead and do that. Or I could do primary rule or secondary rule, right? I could reflect components on the primary side to the secondary side, or I can do the opposite, right? I could reflect secondary side to the primary side. But looking at this circuit, I would rather do secondary side to the primary side. Why? Because there's only one on the secondary side, right? Whereas on the primary side, I have two. So it's less work, right? By reflecting secondary side to the primary side. So that's what I'm going to do. So reflecting the 2 ohm resistor to the primary side. That's what I'm going to do. So how do I do that? By primary rule, I do that simply by dividing 2 with n squared, right? So 2 divided by n squared. Right here, 2 divided by n squared. And then that's the reflected value of the secondary resistance to the primary side. And then once you get that, then I have a new circuit, equivalent circuit that looks something like this, right? 2 divided by 1/2 squared, and then this is 4 ohms. Right? And you can see that 4 ohms and the reflected resistance are in series, so that's why I can just add them up to get me the total resistance. So now the circuit becomes simply this circuit, right? 20 at 0 degrees. Okay. And by doing so, I can find the current. See that? By Ohm's law, I can find current. Current is going to be 20 divided by 12, right? But if you want the angles, right, this is going to be I1 equals to V1 divided by R total, right? That's going to be 1.67. Oops. That's going to be 20 at 0 degree angle divided by 12. Right? That would give us 1.67 at 0 degree angle, if you'd like the angles, right? If you want to include the angles. So that's I1. Any question on I1? How about I2? Well, this is where you need to know the signs. And this is where I made the typo, the mistake, right? Because if you look at the original circuit, you can see that I1 enters the dotted terminal, right? Whereas I2 leaves the dotted terminal. So from our discussion on Monday, if one current enters, the other one leaves, that means the sign is positive, right? So I1, I2 over I1 is equal to positive 1 over n. If one enters, the other one leaves, right? You get the negative sign if both currents enter or both currents leave. But as you can see from this assumption that I made, I1 enters, I2 leaves. Make sense? So it should be positive, not negative. So that's what I have right here, right? Again, I made a mistake by putting the negative sign. This should not be there. So we're going to again get rid of it. So now I2 over I1 is equal to 1 over n, and I2 is equal to 1 over n times I1. If I want to include the angle, that will be 1.67 at 0 degrees, right? That's going to be 3.33 at 0 degrees. So get rid of the sign, minus sign right there as well. Right? Notice that if you include the sign, then it's going to be a different angle, right? Because minus 3.33, that's the same as at 0 degrees. That's the same as 3.33 at 180 degrees, right? So different angle. But again, I made a mistake, so just ignore this. Any questions on this? No? All right. Okay. Yeah, so please get rid of the minus sign just in case you haven't done so. Okay, this next one, which is the last topic, the last section of this chapter, we're going to finish it on Friday, but let's do the introduction part first. The last type of transformer I would like you to know is called auto transformer. Right. What's an auto transformer? Auto transformer is a transformer whose primary and secondary coils are wound on a single winding. Right. So if you have a transformer, typically you would have 2 separate windings like this. Right. But an auto transformer only has 1 winding like this. And then we use like a wiper, right, to tap the winding so that we can form the secondary winding that way, right? Make sense? Or this way, right? So you can put the lower number of windings on the primary side or secondary side, doesn't matter, right? Okay, but the idea here is that you only have 1 winding instead of 2 windings. So both primary side and secondary side are wound on the same winding. That's what's unique about this. And here's a picture of an auto transformer that you would see in the lab. And you see the knob right there, right? So the knob is actually this wiper right there. So you can move this wiper up and down, right? Up or down. Okay. So you can adjust the output voltage basically by doing the having this knob, this wiper. Okay. And then what are the advantages of the transformer? Advantages would be the tap that as I said earlier, that would make it more flexible because then you can have a step up or step down transformer, right? And then as well as the apparent power is actually more than the regular two-winding transformer. And then lastly is smaller and lighter than the equivalent two-winding transformer. Right? It makes sense because it's constructed from a single winding instead of two winding. That's why it's smaller and lighter. However, the big disadvantage is that as soon as you do not have two winding, only one winding, then you're going to lose the isolation, right? If you have a conventional standard transformer with two windings, you could connect the primary side with different ground than the secondary side. You see that? So the primary side could have a different ground than the secondary side. But if you have auto transformer, right, that separate ground is useless, right? Because you can see that both are on the same point, right? So right here, if you put a different ground, that's useless, right? Because those grounds are the same point anyways. So you lose the isolation if you are using auto transformer. And with that, let's stop right here.